When you look at a massive piece of industrial machinery, like a giant power plant turbine or a massive locomotive engine, um, there's this illusion of just total, unshakable brute force.
Oh, yeah. It just looks like pure raw power.
Right. But underneath all that heavy metal, there's actually this delicate, like almost invisible balancing act happening every single millisecond.
And if that balance fails, I mean, the whole system basically tears itself apart.
Exactly. So today we're doing a deep dive into the mechanical brain that prevents that destruction, which is the engine governor.
It's such a brilliant piece of engineering.
It really is. And we've got an incredible set of source materials today, tailored exactly for your inner engineering student. We're using the ME 503 Mechanical Engineering class notes, which were generously provided by Professor Chandan Chattoraj from Dr. B.C. Roy Engineering College.
Yeah, a huge thank you to him for those. They are incredibly detailed.
Seriously. Massive shout out. And our mission today is to reverse engineer this stuff, strip away the confusing jargon, and arm you with the conceptual tools to tackle complex mechanical problems.
I should probably mention Dr. Chattoraj's strict rule at the top of the syllabus, which is attend classes with pen, paper, and a calculator.
Right, yeah. I mean, you might not need the calculator right this very second, but definitely get ready to mentally build some heavy machinery with us today.
For sure. But before we build a governor, we really need to clear up, like, the most common misconception in mechanical engineering.
The classic mix-up.
Yeah. People constantly confuse a governor with a flywheel.
Which makes sense, They both involve spinning heavy metal, they both deal with engine speed, and, well, they both look like giant metal weights attached to a machine.
They do, but mechanically and functionally, they are entirely different beasts. I mean, they solve totally different problems.
Okay, break it down for us.
So looking at the notes, a flywheel's function is strictly about handling speed variations caused by fluctuations in the engine's turning moment during a single cycle of operation.
Let me just pause you there, because turning moment is one of those textbook terms. We're basically just talking about torque, right?
Spot on. Yeah, the actual twisting force on the crankshaft.
Okay, got it.
Because if you think about a standard combustion engine, it doesn't produce power smoothly. It happens in these violent pulses during the power stroke.
Right. Boom, boom, boom.
Exactly. And then there's dead time during the exhaust and intake strokes. So a flywheel is basically a massive physical energy bank.
So it absorbs the extra energy during the power stroke and then pays it back into the system during the dead time.
Precisely. It keeps the speed relatively constant, but only within that single internal cycle of the engine. It fundamentally does not care about outside loads.
Okay, so if we use like a car analogy, the flywheel is essentially your shock absorbers.
Oh, that's a good way to look at it.
Yeah, it's smoothing out the bumpy road of those internal piston explosions so the car doesn't jerk you back and forth. But a shock absorber doesn't actually drive the car.
Right, it can't adapt to a changing external environment.
So wait, if I suddenly hook up a giant industrial generator to my engine, you're saying the flywheel is totally useless for maintaining the overall speed?
It is entirely useless for that specific problem because the flywheel can't generate new energy. It just stores what's there.
Okay, wow.
When you hook up that massive generator, the physical resistance skyrockets. The engine is going to bog down permanently unless something changes.
And that's where the governor steps in.
Exactly. A governor regulates the mean speed of an engine when the external load varies.
So it's like cruise control on the highway.
Hmm.
When you hit a steep hill, the car realizes it needs more power and steps on the gas.
Perfect analogy. The varying demand for power has to be met by the governor physically stepping in and changing the actual supply of working fluid like steam or gas or diesel to the engine.
Okay, but this is the craziest part to me. We are talking about purely mechanical devices. There are no microchips, no digital sensors.
Just metal.
Right.
Well,
So how does a collection of metal rods know when the external load has changed?
it's all about physical logic. Let's visualize the anatomy of a basic centrifugal governor to see how it works.
All right, let's paint a picture for you guys. Imagine a vertical metal rod, the central spindle, and this is geared directly to the engine's output.
So it's matching the engine speed perfectly.
Right. Engine speeds up, spindle speeds up. Now, attached to hinges at the top of the spindle are two downward hanging arms. And at the end of each arm is a heavy metal sphere, the flyballs.
Just picture like one of those spinning carnival rides with the swings. As it spins faster, centrifugal force pushes the swings outward.
Exactly. Now, below the balls, wrapped around that same central spindle, is a metal collar called a sleeve. It spins, but it can also slide freely up and down the rod.
And that sliding sleeve is mechanically linked to those heavy swinging balls.
Yes. And finally, the sleeve is hooked up to a bell crank lever, basically a seesaw. One side is on the sleeves, the other side is connected right to the engine's throttle valve.
It's an unbroken chain of cause and effect. So let's say the load on your engine suddenly increases.
Okay, load jumps up, so the engine has to work harder. Speed drops.
Engine speed drops, so the vertical spindle spins slower.
The carnival ride slows down, so the outward centrifugal force on those balls decreases.
Right, and gravity pulls them inward. They fall closer to the spindle.
And because they're linked to the sleeves, as they fall inward, they physically push the sliding sleeve down the rod.
Which pushes down one side of the seesaw lever.
The other side tips up, physically yanking the throttle valve wider open. More fuel rushes in, power goes up, and the engine recovers its speed.
It is instantaneous physical feedback, no lag. But this whole elegant dance relies on one fundamental physics concept from the notes controlling force.
Okay, controlling force. What is actually doing the controlling?
Well, when the balls are spinning, they want to fly outward, right? That's the centrifugal reaction. But something is pulling them back.
Keeping them tethered.
Yeah. That inward radial force, the one that exactly equals and opposes the outward centrifugal force when the engine is running steady, that is the controlling force.
So they're in a high-speed tug of war.
Precisely. And manipulating that controlling force is how these designs evolved over time.
Right, because the earliest ones, like the Watt governor, just used gravity, right?
Yeah, just the pendulum action of the balls wanting to fall back down. But there's a huge problem with that.
They weren't strong enough for fast engines.
Exactly. At low speeds, great. At high industrial speeds, the balls would fly almost totally horizontal. So a small change in speed barely moved the sleeve. They became totally insensitive.
So engineers had to artificially manipulate that inward force. Which brings us to the classifications in the text, starting with the Porter governor.
The Porter governor belongs to the loaded or dead weight class.
Which literally just means they dropped a massive, heavy chunk of metal directly on top of the sliding sleeve.
It looks like a heavy church bell resting on the collar.
But wait, if you make the sleeve super heavy, wouldn't that make the whole thing sluggish?
It seems like it would, right? But it's a brilliant workaround. By adding that dead weight, the outward centrifugal force has to work way harder. The balls aren't just lifting themselves, they're lifting massive iron against gravity.
Oh, I see. So you have to spin the engine much faster just to generate enough force to get the balls to rise at all.
Yes. The controlling force is now the weight of the balls plus the sleeve. The formula reflects this. The speed squared is basically proportional to the combined mass over the ball mass, all divided by the height.
So it shifts the operating range to a much higher speed while keeping it sensitive. That makes sense. And then the text mentions the Pearl governor.
Right, the Pro-L is a variation of the Porter. It still uses the heavy central weight, but it plays with the geometry.
How so?
Instead of the balls being right at the hinges, the Pro-L places the balls on upward extensions of the lower links.
Okay, so it's using leverage. It gives the centrifugal force a mechanical advantage against that heavy central weight.
Exactly. But both the Porter and the Pro-L have a major industrial flaw. Dead weights are, well, they're static.
Yeah, they're heavy and annoying. If you need to permanently change your factory's running speed, you can't just press a button.
No, you literally have to shut the whole engine down, unbolt it, and swap out the massive iron weight for a new one.
Which is a total nightmare for efficiency.
Total nightmare. So engineers needed a controlling force that was powerful but also adjustable, which leads to the biggest leap in the note's spring-controlled governors, specifically the Wilson-Hartnell.
Okay, so we're ditching gravity and using pure tension. In the Wilson-Hartnell, the fly balls are literally connected horizontally by a massive main spring.
Right across the gap from the left ball to the right ball.
So as the balls try to fly apart, this spring is physically stretching, trying to snap them back together.
And springs can be incredibly stiff, which is perfect for super high-speed engines. But the real genius is the auxiliary spring.
Oh yeah, this is so cool.
It has a second spring attached externally to the lever mechanism.
Which means an engineer can just walk right up to the machine while it's running at full speed.
Yep, turn a hand wheel.
And instantly change the tension on that auxiliary spring. You can dial in the exact equilibrium speed on the fly without shutting anything down.
It's like tuning the engine's brain in real time. It's a huge upgrade.
Now, to actually design these things, you need to speak the language of the parameters.
Yeah.
Let's hit some of the terminology from the notes, starting with height.
Right, denoted by the letter H. And this isn't how tall the machine is.
Right. Well,
It's the vertical distance from the center of the flyball to the point where the upper arms intersect on the central spindle.
Okay, so it's a dynamic mathematical triangle.
Exactly. And then there's equilibrium speed, which is when the forces perfectly match and the sleeve is stationary. And mean equilibrium speed is the speed needed to keep the sleeve dead center.
Got it. The text also focuses heavily on things like effort and power.
Yeah, so effort is basically the mean force that the governor exerts on the sleeve when the speed changes.
Okay, so just the raw pulling or pushing force.
Right. And power is that effort multiplied by the displacement of the sleeve.
Basically, how much actual work it can do to move that heavy throttle valve.
Exactly. Along with things like sensitiveness, how fast it reacts, and insensitiveness, which is the delay caused by physical friction in the joints.
Oh, friction ruins everything, doesn't it?
It always does. But speaking of things that ruin perfectly good theories, we have to talk about isochronism.
Yes. This might be the most counterintuitive concept in the whole deep dive.
Isochronism is this fascinating theoretical ideal. Iso meaning equal, chronos meaning time.
Equal time. Meaning what for the engine?
A governor is perfectly isochronous when its equilibrium speed is exactly the same for all radii of rotation of the balls.
Wait, okay, let me push back on that. You're saying whether the balls are tucked in close or flying all the way out, the speed variation is literally zero.
That's the definition, yes. The required speed doesn't change at all.
But let's test that against reality. Let's take the Porter governor with that heavy dead weight. Can a Porter governor actually be isochronous? Because if the speed doesn't change, the whole cause and effect chain breaks down.
Your instinct is totally right. It's a classic analytical trap. And we can prove it with the formulas. Let's say we have speed n1 when the balls are tucked in, and speed n2 when they're wide open.
And for isochronism, speed n1 must exactly equal speed n2.
Right. Now, in the Porter formula, the required speed is intrinsically tied to the height, h. The only way the math balances is if a specific speed correlates to a specific height.
Okay, so if speed n1 equals speed n2, then mathematically, height h1 must equal height h2.
But physically, what does that mean?
Well, if h1 equals h2, the balls haven't moved vertically.
Nope.
And if they haven't moved vertically, the sleeve hasn't moved.
Right.
Which means the lever hasn't tilted and the fuel valve hasn't budged. The governor hasn't done its job at all.
Exactly. For the Porter governor to change the fuel supply, the sleeve must move, which means the height must change. And if h changes, speeds n1 and n2 have to be different.
So mathematically and physically, a Porter governor simply cannot be isochronous.
It's impossible. It's a great example of using math to prove a physical limitation.
I love that. And actually, looking at Dr. Chattoraj's ME 503 syllabus, there's a big focus on problem-solving techniques. Let's do a rapid-fire review to test our mental models here.
Sounds fun. Hit me.
Okay, factory scenario. A massive load suddenly drops off the engine like a whole assembly line shuts down. Hike me through the mechanics.
The load drops, so engine speed instantly spikes. Spindle speeds up. Centrifugal force overrides the controlling force. Balls fly outward, yanking the sleeve up. The lever tilts, choking off the throttle valve, reducing the fuel until the engine settles.
Boom. Beautifully mapped. Okay, next one. If someone is sketching out a controlling force diagram for an exam, what's the biggest design trap?
The axis convention. You absolutely must plot the controlling force Fc on the y-axis and the radius of rotation r on the x-axis.
Always y-axis for controlling force.
Always. If you flip them, your entire analysis of stability and sensitiveness will be totally inverted and wrong.
Good to know. What about a trap for the Wilson-Hartnell?
Forgetting how it actually achieves its magic. People get hyper-focused on the main spring connecting the balls, but you can't forget the auxiliary spring on the lever.
Right, the external one.
Yeah, the total controlling force is a combination of both. If you calculate the stiffness and ignore that auxiliary spring, your equations will be hopelessly unbalanced.
You can't ignore the tuning mechanism. Makes sense. Well, we've covered some serious conceptual ground today.
You really have.
We separated the cycle-by-cycle shock absorption of a flywheel from the load-adapting brilliance of a governor.
We traced the evolution from the gravity-down Watt to the dead-weight Porter, all the way to the dual-spring precision of the Wilson-Hartnell.
And we mathematically proved why a Porter governor cannot be perfectly isochronous, which honestly leads to this really profound point hidden at the end of the notes.
Oh, yeah. This is my favorite part of the whole text.
So we talked about isochronism as this theoretical, ideal zero-speed variation. It sounds like absolute perfection.
It does.
But the notes explicitly say that a perfectly isochronous governor is actually, quote, not of practical use. Why would perfection be useless?
Because of how it would behave in the chaotic real world. If a governor is perfectly isochronous, it is infinitely sensitive. It demands absolute perfection.
Okay.
So the moment the engine speed deviates even a fraction of a percent, the governor doesn't just adjust slightly, it violently throws the sleeve all the way to its extreme top or bottom position.
Oh, wow. It completely overreacts.
Massively overreacts. It creates wild, violent fluctuations in the fuel supply. The engine would just be hunting up and down erratically, basically tearing its own gears apart, trying to find a perfection that doesn't actually exist.
That is wild. So to function smoothly, the machine actually requires a slight lack of sensitivity.
Exactly. It needs a designated speed range, a slight droop as load increases. It needs a bit of physical tolerance, a bit of imperfection to remain stable in reality.
That is an incredible engineering philosophy to end on. A machine needs a bit of imperfection to survive the real world. It really makes you wonder, how often that's true in other complex systems, or even in our own lives.
Definitely something to chew on.
Think about that next time you're trying to perfectly control every variable around you. Thanks for joining us on this deep dive, and we'll catch you next time.